Okay, so now that we've added and subtracted vectors, we're going to move into 6.3, which is multiplying a vector by a scalar. So a scalar will end up being a constant, a coefficient. So if we look at here, scalar multiplication is multiplying a vector by a scalar. So if I had a vector vector v, and a scalar k, so again, if you want to write down here k, here I can write that down as well. K is a coefficient or a constant. I'll just say constant. You can write both down if you want. So let's say K would be a constant. Then the constant times the vector is a vector that is a scalar multiple of vector V. So what that means is just if I have a vector V, right, multiplied by a number, a constant, a coefficient in front, it's just going to be a multiple of that vector, right? So I guess we might as well use this example down here. So that leads into this first bullet here. So if k is greater than 0, so if k is a constant that's greater than 0, and we'll say greater than 1, because if it was multiplied by 1, it would still be itself, right? So if it was a number like 2, 3, 4, 10, even 1.5, then that k value multiplied by the vector is going to go in the same direction as the vector. So just to hop down here, if I have vector u, so here's vector u, right? It's going in this direction. It's going in the direction of to the right. That's the original vector. And if I had k is equal to 4, just to compare it to the example down below, right? So if I have a constant of 4, which is greater than 0, multiplied by vector u, it's basically just vector u going in the same direction, which is what this is saying, going in the same direction, and 4 of them lined up together, right? So I actually measure that with a ruler, and I would make 4 of them going in the same direction, which just creates a longer vector of u, which is 4 times the size. So that's what we mean by it's a scalar multiple. It's the same vector u multiplied by 4. It's 4 times the size of the same original vector, right? So let's say k is less than 0. So we're talking about a negative number here. So we'll use the value down below. Let's say k is equal to -3. Then that constant multiplied by the vector is going in the opposite direction, right? We know in this case now with vectors that if it was a negative number, negative is making it go in the opposite direction. So again, comparing it to down here, I have vector u, which is this length that I could measure and going to the right. First of all, if it's negative, it's going to be the same length, but moving in the left direction, and then 3 of them, right? So it's the same vector u. The negative means it's moving in the opposite direction, so don't forget that part. And then it's just a scalar multiple 3 times as big as the original vector. So again, vector v and its scalar multiple are also parallel to each other, because if I were to make it 4 times as big or 3 times as big, it's sitting along the same line. So if I were to put the original vector and then the scalar multiple vector above or below it, they're going to be parallel to each other, right? All right, so let's look at what a collinear vector is. Vectors that lie on the same straight line, but once I arrange it head to tail. So first they start out as 2 separate vectors. So let's say I have vector A here moving to the right, vector B here, a different length moving to the right as well. If I were to arrange those, right, head to tail method, and I looked at this example, vector B is equal to a constant times vector A. So I have my original vector A here. Here's my original vector A, but if I multiply it by a constant, if you need to write that down again, I'm taking vector A multiplied by a constant, which is k. So it just means it's going to be what we just talked about, a scalar multiple. Now that k looks, right here we're saying it's obviously a positive value, and that's going to be my new vector b. So vector b is a scalar multiple of vector a, right? So what we're talking about is they would lie on a straight line if I were to arrange them head to tail. So if I were to take vector A, right, and here's the tail of B, here's the head of B, and take the tail of A, I should do this as a straight line, right? And I'm just guessing, again, I could use a ruler here, but you get the point. And arrange it head to tail method. And this is my vector A, just saying that they would make a straight line. They're scalar multiples of one another, or really vector B here would be a scalar multiple of A. Or I guess really you could say that A is a scalar multiple of B, but your multiple would have to be a fraction. So yes, you could have a question coming up in your textbook where it does go the opposite way. You have something that's originally longer, let's say, and you would still say that vector A is a scalar multiple of vector B. You're just saying that then vector A, you're having to multiply by a smaller number than 1, but that's still greater than 0 to go with the bullets above, like half of it or 1/3 of it. So if I look at vector A here realistically and look at it in terms of B, I'm guessing this is probably, the constant here is probably 3, right? Kind of look there. It looks like it's probably 3 times. It's not double. It looks like it's more than double. So K is probably 3 here in this case. So then you would say that vector A is a scalar multiple of B, but multiplied by 1/3, right? It's 1/3 of the size. And again, when they're arranged like this, they would be parallel to one another. So that's just what all this is saying in terms of what would make them collinear. If vector B is a scalar multiple of A, and also the opposite, right? Vector B is parallel to A, then we'll say that vector A and vector B are collinear to each other. So that is the definition of collinear. So this is a separate example talking about linear combinations. If I have a vector U, and that's what we're going to be talking about down here, and I have a vector V, and I have scalars, meaning constants, A and B are just numerical values. They belong to the set of real numbers, meaning they can be positive or negative, fractions, decimals. The quantity, the actual value at the end, if I take the constant times vector U and the other constant times vector V, is called a linear combination of vector U and vector V. And it might make more sense when we look down here. So some properties of vectors. For any scalar, which is a constant, right? A is a number, B is a number belonging to the set of real numbers. And for any vector that I have, vector U and vector V, these statements hold true. So, you know, distributive property, hopefully back from grade 9. So if I have, again, A as a constant, so just a number out here, multiplied by vector U plus vector V. So in brackets, I'm adding vector U and vector V, and we know how to do that from the last lesson. That would be equal to, just to write down here, distributive property, distributing the A, the constant, into the bracket. So just taking the A multiple of vector U and the A multiple of vector V, right? Associative property is, again, these are constants, don't forget A and B. So if I have two numbers multiplied by each other, well, right away I could multiply those and just get one single number, right? Multiplied by a vector, vector V. That's the same thing as taking the vector V and multiplying it by B, and then taking that answer and multiplying it by A. So again, when you're multiplying 2 times 3, or 3 times 2, or 2 times 3 times 2, or 2 times 3 times 2, it's going to be the same thing, right? It doesn't matter when you're multiplying. And the identity property is, again, the V vector is also equal to itself if it's multiplied by 1. So just anything multiplied by 1, we did say that just previously there. It's the identical vector, right? It's just itself. Okay, let's do some examples algebraically. Not too bad so far, but let me know. Write down questions, if you're at home and not in class, so that you can come back and ask me, whether it's during study hall, whether we have a chat open, and in class, same thing. You can always tell me to pause these videos too, right? So we know what a vector is. It has this symbol on top of it. So we don't know the size of them, but that's not the point. We're just adding them algebraically right now. So if I had a vector X and I was adding it to another same identical vector, same length, right? Same magnitude, same distance, moving to the right. It's not negative, right? So it's not moving to the left. plus the same vector x, but a scalar multiple of 2, twice the size. And then I have another vector x, the same thing, same length as the first two, but it's just going in the opposite direction, right? So vector x plus 2 vector x minus 1 vector x. And again, there is a 1 in front there if you want to write that in. It's the same thing as grade 9, guys. We're just collecting like terms. So like terms is the same vector, let's say, same variable of x, vector x, and x, and same exponents, which you're not going to see on here anyways. And then you're going to simplify those like terms and add them together, right? So it's just like adding and subtracting integers. So these are all like terms with each other. They're all related to vector x. So I'm just taking 1 x, let's say, and then I'll just turn it into a vector at the end even. So 1x plus 1x is 2x, 2x plus 2x is 4x, 4x minus 1x is 3x. So really what I'm saying is a constant multiple of 3 times vector x, still moving in that direction because the 3 is positive, right? Let's look at B. So we have 2 different vectors here. We're going to have a vector A and we're going to have a vector B. So we've got 3 times vector A minus 2 of vector B minus 1 of vector A plus 4 of vector B. So again, like terms is, let's kind of color code these. It's always good to have different colors. So let's have, however you want to do that. I'm underlining my A vector and negative 1A vector. And I could underline also on the bottom here or on top my negative 2b vector and positive 4b vector. And again, the sign in front, so the negative belongs with the 2, the positive belongs with the 4, the sign belongs to the number afterwards. So that would end up equaling what? My orange, 3a's minus 1a would be 2, constant multiple of 2 times vector A. And I don't know if it's plus or minus yet, so let's look at my greens. Negative 2 plus 4 would be positive 2 of vector B's. So also the point here is if I was to actually add and subtract these like I was learning in the last lesson, right? I'd be drawing all 4 vectors out and then adding and subtracting them together. So this is just showing why would I do that work when I could simplify first, and then I would just have to draw 2 vectors, vector A and vector B, and make them twice the size, right? And then I could add those together instead of adding 4 together. But it just makes life easier, right? Number 2 here, hopefully I can fit that in without having to erase anything yet. So if I have vector u is in relation to I and j here. So vector u is 4 times vector I minus a vector j. And vector v is 2 of vector I plus 3 of vector j. And I want to write the following vector as a linear combination of I and j. So just write it, instead of in terms of u and v, write it in terms of I and j. Linear combination just means that I'm combining them, adding them together, right, into the same equation. So this is the equation that I'm dealing with. Negative 4 vector u, so a vector u just going in the opposite direction, 4 times the size, plus 2 vector v's. So let's rewrite this. So I have negative 4, and instead of, so this is like distributive property here, I've got u, but u is a combination of, because I want it in terms of I and j. So instead of writing u, I'm writing what u is equal to, 4 vector I minus vector j, done, bracket, plus positive 2 of bracket, v, sorry, I'm going down a little bit here. V is 2 vector I plus 3 of vector j. I want to do the dot and I want to do the arrow at the same time. Then what would I do next? What would you do if this was grade 9, right? So you've got a scalar in front. Just picking my color. I would do distributive property if I was in grade 9. So we're doing the same thing here. We've got a negative 4 constant and a positive 2. So let's do that, and then we'll collect like terms the same way that we would have before. So this would be negative 16 vector i's. A vector I 16 times the size in the opposite direction, and a positive now for a vector j's, plus 4 vector i's. Make sure I can see whether they're positive or negative. Be careful. Plus 6 vector j's. I know I'm not really putting the dot and the arrow at this. just to not get confused, and then collect like terms. So I would probably color code this. So vector I and vector I, and I could even use the same color, but circle, right? Vector J and vector J. That's going to be equal to negative 16 plus 4 would be negative 12. Vector I, positive 4, positive 6, so positive 10 of vector J. And it's already in alpha order. The I comes before J. So I would probably just leave it in that order, even though we've got the negative in front. Okay, let's look at this last example. This lesson luckily isn't quite as long for you guys, so you can have more time to work. So in the diagram, C is the midpoint from W to Z. So as a midpoint, I'm just going to go ahead and put a dot there just to indicate, let me leave it black, just to indicate midpoint. So again, don't mind my circle if it's not perfect. And A and B right here are the points of trisection from X to Y. So you can see here, if I were to put a dot here on A, and I were to put a dot here on B, it's dividing X and Y up into thirds, right? 3 parts by trisection. And midpoint meaning these are equal to each other, just to point out, and these are all equal to each other, dividing it into 3, just saying, right? I don't know why that did that. Express each vector in terms of a linear combination, in terms of a U vector and a V vector. So I've got U vector is going from X to Y. So again, the tail of X, the start of X to the head of W. Did I say Y? The U vector is the XW vector. So let's draw that in. Green, let's say. So starting at X, right, as the tail, let's do this as an actual straight line, and going to W. Right, it is important that you know the direction here. Head to tail is vector U now, because everything that we're writing out for A, B, C, and D is going to be a linear combination of U and V. So we're just changing everything around to be in terms of U and V now, is the point. And let's color code purple. Is going from vector V is going from W all the way to Z across the top there. So let's do that. Tail of W to the head of Z, all the way across is vector V. And everything is going to be in terms of that. Okay, so if I was looking at how can I basically just restate vector AB, so going from A to B, in terms of U and V. So I'm going to color code this again and erase my colors as I go. It's up to you if you keep all the colors in your example. Probably it'd be hard to erase that, right? Unless you did a video of your own note, because then you won't know what was erased. But just kind of be careful here and do color code so that you know that which part of the diagram is answering which part of the question. So for A, let's do, so a totally different color would be blue. I don't have in there. So from A to B, and the direction matters, right? So I have a vector, let's draw a vector, and I'm going to be erasing it after from A to B. Hopefully you can see that blue there. So if I look from vector A to B, it really has no relation to U, but I'm looking that it's more similar, right, to V. It looks collinear, right? It's parallel to it. It's a scalar multiple of it. Because again, if this is a parallelogram and the top is parallel to the bottom and this length would be equal to this length, then AB would be 1/3 of WZ. And now WZ is vector V, right? So if it's 3 parts, I just say that vector AB is then 1/3 of vector V. And you could write that as vector V divided by 3, however you want to do that. Okay, so let's erase, like I said, and do another color. Whoops, I got rid of my black dot there. And And let's do orange. It's not up there yet. So from A to Z. So vector A, it's important you follow the direction, the tail, and the head is at Z. So hopefully you've learned something from the last lesson and the homework that this is clearly not parallel to U. I can't say it's related to U, and it's not really related to V right now. So then when I'm stuck, it's not in the opposite direction or any relation, right? Then you look at this as a resultant. And I look at it as a resultant of, which meaning that this is the beginning, right? That means that was the beginning of my two vectors, and this is the end, the head of my second vector. So that means that the vector and the direction matters has to be drawn like this. And I'm looking to place the two vectors added together to have the resultant along the original diagram, right? In order to relate it to vector U and vector V. So if this was the tail of the resultant, this is the tail of my first vector, right? That's the head. And then I go head to tail method, tail to head, so that the head of the second vector is the resultant head. That's the direction that the resultant goes in. Okay, so I can just say that this A to Z vector is just these two added together. So can I put these two added together in relation to U and V now? Does that help me out? Hopefully it should. So what about A to Y? A to Y is two chunks of the three, so 2/3 of V, right? So 2/3 of vector V, because they're parallel to each other, plus, I might change that to a minus if I had to, but plus, just to show that it's adding these two vectors together. Y to Z would be parallel to vector U, so plus vector U. And just to go over here again, these are not like terms, right? So I can't put them together when I have two. I have to look for like terms like I practiced just in the previous question. Same as grade 9 in order to combine the like terms and simplify, right? Okay, let's go to, trying to see how I can have the diagram for C and D. I'm just gonna move that up. So stay with me here. I'm going to erase this. I'm going to erase my orange, like I said. So we still just have the original vector U and vector V to compare it to and erase this, but I'm going to put C and D here instead. So if you can just work with me there. Let's do brown. Just so I don't have to move the diagram out of the way. Okay, so now we're on 2 left. We're looking at question C, which you can see in front of you, is vector A to B. Just double check that on my page, yes. WB. So WB, let's draw that in, that vector. W to B. Again, we're kind of going through the middle of the parallelogram here, not along the sides, which is the easier way to do it, but that's fine. Just means we have to find another way to go about this here to find out vector WB. So it's not parallel to any of the green or purple vectors. So I want to start at the tail of vector WB and move towards X, and then go from X to B to get to the head of vector WB, right? It has to, the direction does matter here, right? Because if this is the tail, this is where the tail, the start of the first vector, those are the rules. And then I go head to tail, and the head of the second vector has to end up where the head of the resultant vector is. So now I want to see if this is helping me out to just add these two vectors together in order to get this WB vector resultant. So if we start in order, now what do I have to say here? So vector WX, so just to write out, we're really doing vector WX, right, in order, vector XB, and adding vector XB together. But we want it in terms of U and V. So vector W to X is vector U, but hopefully you see that it's in the opposite direction, right? So it's just the negative of vector U. It's just going in the opposite direction, that's all. And then from X to B is going this way, which is the same way that V is going, and it's 2/3 of it, right? So again, 2/3 of vector V. So somewhat similar to B. We just have that opposite now included in, and these are not like terms, so I can't go any farther. Hopefully not too bad. Now D, the final one, we've got vector A. Well, I should do this in a different color. Let's do that. Let's erase Oh, can I get that one without the green? Close. Let's put the green back. Vector XW this way. All right, now let's go with color. Let's do yellow. You probably aren't gonna see. There's not a lot of color options here. I guess I'll go red. I haven't really done red. And question D is vector A to C in terms of U and V. So let's draw that in. A to C. All right. Now be careful. That's one of the reasons why those dots are there, to really help you out. I'm hoping that you're seeing that A to C is not parallel to U. So I would not say that vector A to C is just the same thing as vector U. They're a little off, right? They're not parallel. It's not the opposite direction. It's not related to vector V at all. So again, I kind of treat this as a resultant. But to get a resultant, I have to go along the outside, the original shape. So I can't go cut from A to W and then W to C, just because that's more work for me than I have to figure out A to W. So instead I can do, if you see here, I'm going to have 3 vectors added together. So again, if this is the tail, this is my starting point. I have to go along A to X vector, then head to tail X to W vector, and then W to C vector to end up with that resultant. So I'm just adding those 3 together. So let's take a look at vector A to C. Would be A to X, right, is going in the opposite direction of vector V, and it's 1/3 of it. Now we're getting used to. So I'm just going to say negative 1/3 of vector V, because opposite direction. And then this is going in the same direction as U, so plus just a positive vector U, plus I'm adding same direction as V, and it's half of it, right? Half of V, 1/2 of vector V. And then the additional part here is that we do have some like terms that we can put together, because we have vector V, right? Vector V. And U is just going to be hanging out. So just to put these together, I have 1/3 vector V plus 1/2 vector V, and then just adding in the vector U that's on his own. So I need an LCD here. Just like always, again, relating back to grade 9, I need a denominator of 6, vector V. I'm just finishing it off, vector U, vector V, because that's not going to change. So I'm timesing by 2, right? Times 2, negative 2, times 3, there we go. And finally, if I have negative 2 vector V's plus 3 vector V's, that ends up with positive 1. So 1/6 of vector V's plus an entire vector U. 1/6 vector V's plus U. And now it's totally up to you. Again, that's basically the end. Depending on the back of the book or a worksheet or however it's written, or for yourself, if you like it in alpha order, then you need to put the U first, right? So that's probably the case for when you're checking your answers. So vector U plus 1/6 of a vector V. And there's your linear combination.